Hello students, myself Amrita Dhar, Assistant Professor of Electrical Engineering Department of Greater Kolkata College of Engineering and Management, JIS Group.
In this video, I will discuss about different types of electrical heating and resistance heating. This topic is included in Module 3 of the subject Utilization of Electric Power. Subject code is EE702. In this video, I will discuss about electric heating. Electric heating. This is a new module. When we know that electrical energy in thermal station is obtained by converting thermal energy to mechanical energy and then to electrical energy, it seems logical conclusion that conservation of electrical energy back into thermal energy after losing efficiency at each converting stage will be very much less efficient than directly employing the thermal energy for heating purpose. However, when we take efficiency of utilization and other factors into account, we nevertheless find electrical heating still holding the winning position over the other methods of heating. So first we discuss about advantages of electrical heating. First we discuss about advantages of electrical heating. Okay. Advantages of electrical heating. Now first point is cleanliness. Cleanliness. Okay. In the absence of dust and ash of the fuel, charge never gets contaminated. Second advantage is absence of flue gas. Absence of flue gases. So in the absence of flue gases and soot, atmospheric and charge are not polluted and we thus get clean and hygienic operation. Okay. Next advantage is ease of control. Ease of control. Now we can easily control the temperature of charge either manually or made fully automatic, and we can also adapt heating and cooling cycle. So controlling of temperature of charge is very much easier. Next is cheap furnace. Next is cheap furnace. In the absence of chimney and grating, electric furnace, specially requiring protective atmospheres, are cheap. Also, maintenance required by these furnaces is very small as there are no flue ports or pipes and insulation presence. No problem. Okay. Next one is better working. Better working. Better working conditions. Now, as the radiation losses are low, working with electric furnaces is very convenient and cool. Moreover, these furnaces are noiseless in operation also. Next is ease of adaptation. Now, electric heating can be adapted easily to our requirements of heating, such as heating local spots or heating material uniformly. So, our next point is Next point is very high efficiency of utilization. Okay, in electrical heating, source of heat can be brought directly to the point where heat is required, thereby reducing losses and increasing the efficiency. Further, there are no products of combustion which involve heat losses in their removal from combustion chamber. Next is uniform heating. In all the methods of heating by burning fuels, heat is to be conducted from the outer surface of the material to inside of the material. Thus, inside core of the material comparatively remains cold, and by electric heating it is possible to generate heat inside the core of the material, and thereby uniformity in heating is closely achieved. Last is heating of non-conducting materials. Non-conducting materials. It is possible only with electric heating to get non-conducting materials heated uniformly throughout the section, and this is possible because heating is generated inside the material itself. Okay, so first advantage is cleanliness, second is absence of flue gases, third is ease of control, fourth one is cheap furnaces, fifth one is better working conditions. Then ease of adaptation. Next advantage, very high efficiency of utilization. Next advantage is uniform heating. Next advantage is heating of non-conducting materials. So these are the 9 advantages of electrical heating. Okay, next we discuss about different types of heating methods. Okay. Methods of electrical heating. So first we divided electrical heating in power frequency heating and high frequency heating. Next, power frequency heating is divided into resistance heating, arc heating and electron bombardment heating. Resistance heating is further divided into direct resistance heating and indirect resistance heating. In this video, I will discuss about resistance heating, direct resistance heating, and also I discuss about indirect resistance heating. Next, arc heating is also divided into direct arc heating and indirect arc heating. And high frequency heating is divided into induction heating and dielectric heating. Okay, so these are the different heating methods. So I start with resistance heating. Resistance heating. Now when electric current passes through a resistance, power losses take place. Therein which appears in the form of heat. So power loss is equals to I square R watt. This is equals to I into V because V is equals to I into R. So in place of I into R we can write V. And this is equals to V square by R because I square is equals to V square by R square. R and R cancel out. So this power loss we can write power loss equals to V square by R also. Where R is the effective resistance of the element. Now, unlike induction heating and dielectric heating, resistance heating works equally well with low voltage and low frequency supply even with DC. In resistance heating, all the energy given to the heating element is converted to heat, and there is loss of energy only in delivering the converted energy from heating element to the heating load. And in high frequency heating, there is loss of energy at two stages. First, while converting power frequency supply to high frequency supply, and second, while transferring high frequency power to the heating load. Thus, overall efficiency of resistance heating is high, and this makes resistance heating competitive with other methods of heating employing fuels. And in addition to above, resistance heating method is favored on account of uniform power demand, giving a good load factor and almost unity power factor. Okay, so this is all about resistance heating. This is the basic concept of resistance heating. Now I discuss about direct resistance heating. Now, in direct resistance heating, electric current passes through the charge itself, and thereby this is one of the most efficient methods of heating. This method of heating is employed in salt bath furnaces and in electrode boiler for heating water. Now, salt bath furnaces are used for the purposes of carbonizing, tempering, quenching and hardening of steel tools. And heating in salt bath furnace eliminates oxidation, gives rapid and uniform heating, and it is possible to have selective localized heating. Depending upon the type of salt used, temperature of salt bath may range between 1000 to 1500 centigrade. For temperatures up to 1000 centigrade, furnace pots are of mild steel and electrodes are of mild steel. And for higher temperature, material lining is used in pots. And voltage used ranges between 2 to 20 volt and current up to 3000 ampere. Okay, and AC supply is usually used as low voltage can be obtained by step down transformer, and voltage on the secondary side is changed by tap changing gear inserted in the primary of the transformer. And to start dry lumpy salt in the pot, the pot does not have required conductivity, and therefore to start the salt bath furnaces, provision of current conducting bath between the electrode is usually done by bridging a piece of carbon between them, and or by melting a pool of salt around the electrodes, or by transferring molten salt from furnace already under operation. Now, as the temperature of bath increases, the resistance goes down, and therefore these salt bath furnaces are started with highest tap, and as heat proceeds, this is gradually brought to the lowest taps to keep the current within required limit. And control of current is also affected by varying the depth of the immersion and distance between electrodes. And it is essential to have good depth of immersion in order to prevent variation in current due to changes in the level of the salt caused by either inserting or removing charge from the bath. Okay. Now when highly conductive metals are used insertion of electrodes into charge would now mean direct short circuit, and to avoid this, in such cases highly resistive powder is sprinkled in between the surface of the pieces, and more heat is therefore produced and these contact surfaces. So this is all about direct heating. Now we discuss about indirect heating. Now, electric current is passed through an element of high resistance. Passage of an electric current through resistance produce I square R loss, which manifests itself in the form of heat. So, heat is then transferred from the heating element to the charge mainly by radiation and convection and rarely by conduction. Examples of indirect resistance heating will be found in the room heater, hair dryer, soldering iron, flat iron, immersion heater, hot plate, frying pan, electric kettle, electric toaster, electric water heater, electric oven, etc. Okay. Next we discuss about types of furnaces. Types of furnaces. Now, one way of classifying resistance furnaces is based on working temperature. Low temperature furnaces up to 300 degrees centigrade, also called ovens, and are mostly used for drying varnish coatings, vulcanizing and hardening of synthetic material. And these are also used for tempering hardened steel pieces. Medium temperature furnaces having working temperature between 300 degree to 1500 degree centigrade. 300 degree to 1050 degree centigrade, and are used for annealing, normalizing of steel and non-ferrous metals, and melting of non-ferrous metals and stove enameling. And high temperature furnaces having working temperature between 1050 degree to 1350 degree centigrade and are used for hardening purposes. And typical furnaces employing heating element and having provision of carrying out heat in particular atmosphere shown in this figure. Now, resistance heating using metallic resistor is widely used for particular atmosphere is shown by this figure. Okay. Now, resistance heating, usually metallic resistors, is widely used for heat treatment, but the temperature associated with metallic resistors are not high enough for melting most of non-ferrous metals and cast iron. Graphite can, however, be used at much higher temperatures. If satisfactory means are provided to reduce the rate of oxidation to minimum to compensate for increased resistance as wear takes place, and to replace the graphite resistors easily and quickly when its useful life is complete, full benefit can be taken of the advantages of resistance heating over high temperature working range. And rocking resistor furnace, as manufactured by Messrs. Burlefco of England using graphite resistors, you can see in this picture. It consists of a cylindrical shell with detachable flanged end. For ease of lining, the furnace is designed to rotate on the rollers sixth number part is to enable the body to be rocked backwards and forwards. The refractory lining shown by point 5 is built into the shell to reline the furnace, and the shell is lifted off and the rollers are turned vertically on the end, and the top end cover is then removed and the lining material ramped round suitable formers. Graphite resistor shown by point 2 is arranged along the horizontal axis and is held in place by two large diameter holders pointed by 3, also made of graphite. One of the holder, which is detachable, has the resistor fitted in a plug socket, while a conical connection is made with other. The graphite holder passes through close-fitting refractory tubes and properly designed sealing rings pointed by 8 prevent the ingress of the air, and the holders are mounted in free-moving spring-loaded carriages pointed by 7, so that good electrical contact is always maintained, and the carriages are separate and then remain stationary as the furnace rocks, and robust connection are made to the holders and stationary, and large flexible cables are used to carry the heavy electrical current, which is supplied from a special transformer with tappings on the primary winding, so that the voltage can be adjusted on the secondary to compensate, and for the increased the voltage can be adjusted on the secondary to compensate for the increased resistance as the resistor wears, and it is thus possible to maintain almost constant power input. One end of the carriage is specially arranged so that it can quickly be run out away from the furnace cell, and which enables the resistor to be changed in a few minutes, and the carriage may also be run out when the furnace is charged, so as to avoid possible damage to the resistor, and a detachable door above the spout is provided for charging and to equalizing lining, where the body may be reversed in its roller. Okay, on the passage of current, the graphite resistor is heated throughout its entire length, and thus heat is evenly distributed in the furnace and radiated on the cold charge and furnace lining. As soon as charge melts, the furnace is rocked backwards and forward to absorb the heat from the refractory lining and to mix the metal. Provision is usually made for automatic control of rocking motion, and the amplitude of which is adjustable. The white hot graphite resistor gives good reducing condition, and no slack covering is necessary to prevent oxidation, and these reducing conditions permit very high yield when alloys such as cadmium, copper containing a readily oxidizable element have to be made. Now, unlike Ajax watt furnace, you can shown in this picture, rocking resistor furnace can be completely emptied, and this furnace is considered superior to rocking arc furnace. Now, rocking arc furnace on some points, the points are life of the furnace lining is more as intense, local temperature of the electrical arc is avoided. Second point is due to even temperature distribution, heavy loss of volatile elements is avoided, such as zinc in brushes. Third, it has better power factor resulting in lower electrical bill. And fourth one is there is no noise due to arc. Okay, now we discuss about requirements of a good heating material. Requirements of a good heating material. Okay, first is it should have high resistance, so that small length of wire may be required to produce a given amount of heating. So it should have high resistance. Next, it should have high melting point. It should have high melting point. Next, it should not oxidize. It should not oxidize at temperature of furnace, otherwise we will require frequent replacement of the element. And last characteristics is it should have low temperature coefficient. Low temperature coefficient, so that at starting from cold it should not take heavy current. Okay, so these are the 4 requirements which we generally find in good heating material. Next topic is different type of heating materials. Okay, now here depending upon the service conditions such as maximum operating temperature, we have different types of alloys for heating elements. Now you can see in the in this table these alloys are basically divided into 4 classes. Okay, nickel copper, nickel chromium iron, nickel chromium and chromium aluminum iron. So as per composition, in nickel copper alloy, nickel is about 45% and copper is 55%. In nickel chromium iron, the amount of nickel is 60%, amount of chromium is 16% and amount of iron is 24%. In nickel chromium, amount of nickel is 80% and chromium is 20%. And chromium aluminum iron, the percentage of chromium is 20 to 30%, aluminium is 5% and iron is 65 to 75%. Next, maximum temperature of operation. For nickel copper alloy it is 400 degree, for nickel chromium iron it is 950 degree, for nickel chromium it is 1150 degree centigrade, and for chromium aluminum iron it is 1150 to 1350 degree centigrade. Specific resistance at room temperature of 20 degree centigrade. The specific resistance for nickel copper is 49 micro ohm per centimeter cube. For nickel chromium iron it is 110 micro ohm per centimeter cube. For nickel chromium it is 109 micro ohm per centimeter cube, and from chromium aluminum iron it is 140 micro ohm per centimeter cube. And specific gravity for nickel copper is 8.88, for nickel chromium iron it is 8.28, nickel chromium it is 8.36 and 7.2 is for chromium aluminum and iron alloy. Now nickel copper alloy is frequently used for heating elements operating at low temperatures. It is most important property is that it is virtually zero resistance temperature coefficient, and nickel chromium alloy is cheapest and most economical for temperatures up to 950 degrees centigrade. Nickel chromium alloy has not only good resistance to oxidation up to 1150 degree, but at the same time it has sufficient strength. And on the other hand, iron chromium aluminum alloy, Kanthal is the trade name, has very good resistance to oxidization at high temperature but lacks strength. Okay, so as such elements of this metal require more support. Various forms of silicon carbide are used for temperature up to 1400 degrees centigrade. For still higher temperature, platinum, molybdenum or carbon can be used as resistors. So these are the different types of heating materials. Next is causes of failure of heating elements. First is formation of hot spots. Okay, so this is the first type of failure. So formation of hot spots. Hot spots are the points in heating element which are at a high temperature than the main body of the element. Hot spots may be due to any of the following. Hotspots may create due to various causes, such as high rate of local oxidation may reduce the cross-sectional area of the element wear, thereby increasing the resistance at that point. This will produce more heat locally, give rise to breakdown of the element. So first is high rate of local oxidation. Next is shielding of element by supports. Next is shielding of element by supports, etc. will reduce the local heat loss by radiation and cause a high rise of temperature of shielded portion of the element, and thereby minimum number of supports without producing distortion of the element should be used. Next causes of formation of high spots is due to too high element temperature. So due to too high an element temperature, insufficient support for the element, or the selection of wrong material, sagging and wrapping the element may results, and this sagging and wrapping may causes uneven spacing of section and thereby producing hot spots where section are closer together, or even there may be actual shorting of adjacent section of an element. Next point is, next failure is oxidation and intermittency of operation. Now at high temperature, oxide scale is formed on the surface of the heating element, which is continuous and tenacious. The oxide layer is so strong that it prevents further oxidation of the inner metal of the element, and however, if the element is used quite often, the scale is subjected to thermal stresses produced by frequent cooling and heating, and thus the oxide scale therefore cracks and flakes off, exposing further fresh metal to oxidation, and this will produce increased local oxidation, producing hot spot. Next cause is embrittlement due to grain and growth. So all the heating alloys containing iron tend to form large brittle grains at high temperature, and when cold, the elements are very brittle and liable to rupture easily on the slightest handling and jerks. And last causes of failure of heating element is contamination and corrosion. Elements may be subjected to dry corrosion produced by their contamination with gases of the control atmosphere prevailing in annealing furnaces, or fumes from flux used in brazing furnaces, or oil fumes produced by heat treatment of components contaminated with lubricant, and all the condition mentioned in this video which determine the life of the element most critical are temperature of the hottest point and ratio of intermittent to continuous working. Okay.
That's all from today's class. If you have any problem, please contact with me. My contact details is given on the first slide. Thank you.